Kathleen M. Vandiver, PhD. Kathleen Vandiver enjoys creating science lessons that teach abstract concepts in concrete ways. She is the director of Community Outreach Education Core at MIT's Center for Environmental Health Services and a curriculum developer for MIT's Edgerton Center. Kathy's training includes a PhD in cell biology from Tufts University Medical School and an MA in education degree from the Harvard Graduate School of Education. Prior to MIT, Kathy taught middle school science for 16 years in the Lexington Public Schools. In 2011, Vandiver was inducted into the Massachusetts Science Educator Hall of Fame by the Massachusetts Association of Science Teachers, or MAST, a Lifetime Achievement Award. And without further ado, I'd like to present to you Kathleen Vandiver.
Hello, everyone. This is a wonderful time that we've just had thinking of all the big picture, and now I'm going to move to using and talking about atoms. And that's what the brick by brick is, because we're going to use bricks as atoms to look at ocean acidification. And I'm going to ask you to get your things ready because I'd love to dive in, so to speak. And I have my own little periscope, it looks like here, but this is actually a homemade document camera. And I often use it to teach because I can have students actually have them too. So anyway, I'd like for sure for us to set up our materials. And I'm going to switch to showing you our mats. So I'm hoping that you can get them out. We'll put the normal ocean chemistry mat on top and then the ocean acidification one underneath. We'll do them in that order. And I want to let you know that I'm going to be working as if you are my students for most of the time, and we're going to work together to actually follow what's causing ocean acidification. And we'd like to start off, first of all, by thinking a little bit about the normal ocean and the normal chemistry. And it's great that Joellen had talked about how our oceans have been absorbing so much carbon dioxide. After all, it's a huge amount of surface of our planet is ocean. So I'm hoping I'm hearing some bricks and you have them next to you. And this is part of a set of many examples using bricks as atoms. There's one on air pollution, there's a lot of other ones, and this one just fit right in for your program today. So that's the reason why I'm starting with it. So right now, I think it would be really great if I'll point out that this is the normal ocean chemistry mat, and the instructions here say that we're going to follow the numbers for two different chemical reactions. And I'd like for you to locate them on your mat as well. You can actually see that there's a blue line going all the way across in the middle, and that one is called making bicarbonate. And then you can also see that we've got blue numbers, 1, 2, 3, 4. Those are the steps we're going to follow in order to recreate this chemical reaction that's in the water. You can also see that there's a second chemical reaction below, and it's called making chalk. And it was great Joellen mentioned chalk as well, because we're going to be making chalk and thinking a little bit more about its role in the ocean too. All right. So those are the two reactions we're going to do. And we're going to start off by making carbon dioxide. And I'm hoping you have your bricks out, and I'm going to move along with making them with you so that I can make sure that you are following along. So this is our carbon dioxide. You can see that just like in chemists always do, carbon is black and oxygen is red. So that's how we get CO2. And we don't care about the bonding levels right here. This is an introductory representation. So you can see that the oxygen is attached to the carbon, and this carbon attaches to this oxygen. And it's a linear molecule too. So let's place that in the in the air right here. Number 1, a small amount of carbon dioxide is normally present in the air. Build one CO2 molecule and place it on its picture in the air. And students like this because they get instant satisfaction that they made it right, okay? 2, we put it on the picture. 2, the oceans absorb CO2 from the air. Now we're going to move the CO2 molecule into the ocean as shown with a dotted line. Blip, 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 blip. Yep. And now we build one H2O molecule and place it on its picture to represent all the water that we have in the ocean. So now we've set up our reactants, if you're with me. I can't see you all. I wish I could. So anyway, we are now going to put together our reactants of carbon dioxide and water. And you can see the arrow here showing it's a chemical reaction. Now remember, in a chemical reaction, it's not defined by fizzing or anything else like that. It's defined by its definition with the atoms, or the bricks in this case. What happens is, in a chemical reaction, that the atoms get rearranged into different groups. And so that's what's happening here. This is a chemical reaction. So carbon dioxide and water react to produce carbonic acid. So take apart the CO2 and the water molecule and use the molecules to build one molecule of carbonic acid as shown and place it on its picture. And if you have trouble building this, you can actually see it's a top-down view. You can go to the small lower left-hand pictures and you get some help there. So you get two like this, and we get carbon going across the top. It's almost like a little diving board. Actually, this is the way the 3D pictures actually look for carbonic acid. These are all attached. The correct atoms are all attached to each other, and we've got it on our picture here. So this is H2CO3. And you can see that you're teaching a lot about making formulas as well. So the 2 follows behind the H and indicates that they're 2 hydrogens. The hydrogens in the carbonic acid are not tightly attached. One hydrogen can easily fall off. So we see this is a reaction again. So take off one hydrogen from the carbonic acid molecule, place the hydrogen on its picture and the bicarbonate on their pictures, and we're going to leave them there right now for this first reaction, okay? All right. I did that quickly. I'm hoping you're catching up. All right, so next thing we're going to do is move along to the second reaction. And in this one, we need to show that calcium and carbonate are molecules that are dissolved in ocean water. Build the models of calcium and CO3 as shown and place them on their pictures. So I've got my calcium, and these are dissolved in the water. And now we're starting the second reaction. That's why we're using new bricks. Second reaction, making chalk. So we've got a carbonate ion, and it includes these atoms that are bound together. And that looks like it's in the water as well now. And now we can see we're going to have a chemical reaction. So we're going to read step 2. Creatures in the ocean take calcium and carbonate from the water and build chalk. So add calcium to the CO3 as shown and place the model of chalk on its picture, and then we'll read the conclusion. So now, oh, this is really cool. It turns out chalk is solid. So this is really a different reaction which shows how clearly we've made a new product. But the conclusion is very important. Why in the ocean is making chalk so important? Well, here's the conclusion, and I'm reading it. Making chalk, biomineralization, is a very important process in the ocean. Seashells and coral reefs are made from chalk. We've learned the important coral reef that is disappearing near Australia. But normal ocean water has the correct balance of free hydrogen and carbonate molecules for living creatures to make chalk. So chalk is really adding up to making shells and coral reefs, and you can see that Nemo here is really very happy with all the chalk that's created in the ocean. So this explains a little bit about normal ocean chemistry. And now what I'd like to do is I'm going to put these back over in my molecules pile over here, and we're going to see some differences when we've been burning a lot of fossil fuels, what is going on. Because not a lot of people realize that ocean acidification actually is associated with the amount of CO2 in the air. So it's really nice that this can help us make the point about what's going on here. So this mat, I'm just taking apart my atoms here on the left to get ready to go. We're going to use a lot more, and I hope you've got your hands ready to do some building. Okay, so we're going to move along a little faster now, since you know We're going to follow the numbers for the two different chemical reactions. We have one making bicarbonate. It looks like we're going to get a lot of CO2 in this picture, okay? And the second one actually says making less chalk across the bottom, and we're going to see why this happens. All right, you get started building your CO2 molecules. I'm going to speed along too. You can imagine kids really like to do this, and we try to make sure that everyone stays together so we can be sure that we arrive at the conclusions at the same time. All right, so I've got my CO2 ready. Every day, more carbon dioxide is released into the air from the burning of fossil fuels. Build 3 CO2 molecules and place them in their mixtures above the air. And then number 2, oceans absorb more CO2 from the air. Move the carbon dioxide molecules into the ocean as shown. And now we're going to build 3 waters. And these are our reactants now. We've finished 2. You may not have noticed it originally, but anything that is an action is always done in bold. And anything here that's written in the regular type print is really explanation about what's going on. So number 3 over here, we're going to get the reaction now. Carbon dioxide and water react to produce the carbonic acid that we saw before. So take apart these all together, and we're going to make these molecules here of carbonic acid. You had your practice one earlier, so I'm hoping this becomes quick for you too. And it helps if kids work in teams of 2, which is usually how we teach this, with one box of bricks and then 2 kids to a mat. And this works very well. And one more. Wow. You can see that we're using the same bricks, and this is really clear about chemical reactions, that they are rearrangements. And you see I've got no bricks left over. Kids are always really excited when they discover, look, it works, it's got no atoms left over. Here we are. All right, so now we've got carbonic acid. Now here's something that's really important. We're going to see a lot more hydrogen in the action here. The hydrogens on carbonic acid are not tightly attached. One hydrogen can easily fall off. Take off 1 hydrogen from each of the carbonic acids. That's what I'm doing now, pulling off 1 and then laying them down. And I've got 3 there. Remember, in the other one, we only had 1 here. Okay, so we've continued and finished making bicarbonate, and now we're going to get into the second chemical reaction, so we'll start with new ones. Here we go, making less chalk. So this is what's dissolved in the water. Carbonic acid, carbonate here, sorry. And we've got calcium also, because there are lots of salts that end up with calcium ion. A lot of salts are available, and of course in salty oceans. And now what we do is notice that up here, there's so much hydrogen. More CO2 in the air has created a lot of free hydrogens over here. And so we move 1 hydrogen into the dotted line here. And this part of the story is very interesting. Too many free hydrogens interfere with the normal ocean chemistry. So what happens is, the hydrogen beats out the calcium in this case, and the calcium remains in the water. So now we can see that when we read the conclusion, burning fossil fuels releases CO2 into the air. Adding CO2 in the air additional CO2 in the air is absorbed by the ocean, and more free hydrogens are created. The process of creating more free hydrogens in the ocean is called acidification. When acidification occurs, free hydrogens bond with the carbonates, making it harder for sea creatures to make chalk. Weaker shells are produced, and then there are fewer healthy coral reefs in the ocean. And this was so sad, we had to make Nemo here all alone and kind of looking sad. So this is the first part of understanding about ocean acidification, is getting the general idea that this process of making chalk is much harder for many creatures in the ocean. And that's going to change the ocean quite a bit. And so I'm hoping you had some idea now about these hydrogens. And most young people, I'm talking about middle school particularly, how do you teach how to grasp something about pH? So what I'd like for you to do is, we made one other side of this map, and it shows how oceans and the pH scale can be taught very, very simply. And in the future, if you would like to add a lot more detail, I think even doing it this way, even for older students, kind of gives them a real graphic in their mind, and so it's quite useful. So it's exciting, first of all, to find out there's a question like, what is pH? And what we're going to do right now is follow through with making a model of two liquids. And we're going to put hydrogen in the picture. And it's kind of fun for kids to find out that the H in pH actually means hydrogens. So what we're going to do is use a lot of our white bricks, of course, which are hydrogen, and we're going to put them in this picture, and we're going to make a model of two liquids. One looks like it has 10 hydrogens in it. This doesn't require much building skill, let me tell you. Anyway, so we get in 10 here. And then we just put 1 in this one. So we use the pH numbers actually to describe acids and bases. And when acids have many free hydrogens and bases have few hydrogens. So it's very easy to look at this and say which one is more acidic. It's very simple and straightforward in the sense of figuring out it's a lot of hydrogens versus fewer. But this little simple diagram does help you realize, many students realize, that the numbers in pH are really referring to a tenfold change. And this is really important because when you look down at oceans and you see that their pH numbers have only changed slightly, you think, well, why should we worry? So it's going back and understanding a little bit more about the pH scale is really useful. So this is here as for more advanced students to just review for them the idea about the exponents and understanding that the pH numbers are really very, very highly in the number of hydrogens. And in fact, I think if we move over to part 2 over here, you can see that the numbers on the pH scale may surprise you. Liquids with low pH numbers have lots of free hydrogens. So you can see this little graph I'd like to show you. It's not a graph, sorry, a little scale. This side, where the numbers are very small, you can see all the white hydrogen ions there, whereas on this side you can only see 1. So this is the basic and this is the most acidic. And the pH scale sometimes is really hard when people talk about high pH, low pH. You don't know really, it's quite confusing to figure out when you're first a novice in this thinking. So what I started to do was just give students a thing that they could do. For instance, is to point to the number of the strongest acid. You can actually see, oh yes, like this picture over here, we've got lots and lots of hydrogens. So these numbers that are very small actually mean lots of hydrogen. Point to this number with the strongest base. That's 14, so it goes from 0 to 14. And then it's kind of interesting to look at a couple things that most people do in trying to get people to understand the scale, is like coffee, is it an acid or a base? I can find it here. But people don't oftentimes use the example of ocean water. So I put ocean water on here because we're looking at oceans. And you can see that ocean water actually is slightly basic. So we've got it at 8 here and going more basic in this direction. So there's ocean pH. So you start with a real visual picture, then we move to moving more with numbers. And now you can see we're thinking a little bit more about changes and representing how much change is happening in oceans. And this is a very simple diagram showing that in the past, like the past oceans in 1910 or so, were known to have a pH of about 8.2. And it's hard to, that's a pretty good number to start with for a baseline. And right now, when I made this map up in a present day ocean, it was 8.1. So let's just start by making and putting some representative numbers of hydrogen on here. We're going to see a small change in pH number and what happens to the number of hydrogens that are become dissolved in the ocean. So it turns out that in the present day ocean, if it were 4 hydrogens over here, we have an increase in about 25% more free hydrogens right now as we speak in the oceans. They are absorbing so much CO2. And in the future, if we're predicting pH, 7.8 doesn't seem like much of a change from 8.2, but you'll notice we've more than doubled the amount of hydrogens that are in the water. So we're going to end up with 10 as a visualization for the increase. It's really hard for non-scientists to see that the relative change is much bigger than they probably expect. All right, and so the final steps are really talking about why do we care about ocean pH, and I think all of us are pretty clear about why, but it's nice to actually have another visual in this story. And so you can talk about, everybody always talks about, too many times in curriculum probably, about food chains and things like that, but the ocean pyramid is really important. And our plankton down here, we know that our predators at the top certainly depend on every other lower layer. So a small change in ocean pH can affect many sea creatures. For example, if the tiny plankton with shells in the ocean fail to grow, many creatures that eat plankton, like fishes and whales, may die out. So I want to end on a very positive note. So here we go. What can we do? So we have to reduce the amount of CO2 released into the air by burning fossil fuels. We can produce energy from solar and wind instead. We can help keep the oceans healthy and keep people who depend on fish for, we can conserve electricity, recycle, bike or walk instead of driving. And these actions will help keep the oceans healthy and help people who depend on fish for food. There are a lot of countries that depend on fish for food. And if you look in here, you can actually see that there are fewer fish being present as the oceans become more acidic. From what I have read so far, the main winner in this ocean acidification is jellyfish. So I would like to point out that I don't know how jellyfish taste, but we've got a lot more jellyfish in our future, I think. So we need to work together for the planet, and these little pictures down below show you that these are things you could ask students what they represent maybe and how they end up helping. So that's kind of a summary activity here on the last mat. And these mats were designed basically for middle school introduction to ocean situations and acidification. But we have found that they make really great, very useful public outreach examples when you're doing things with high school students, if they're stopping in to visit a marine biology place or something else like that, to have this as a summary exercise for giving people with a real close-up picture of what's going on. And thank you so much for for providing all this to all the teachers. I was really excited about it. And I just wanted to point out that, I'll go to my face cam now, sorry, that there are a lot more lessons that have to do with air pollution, and they're much simpler than these. They're the ones that one would start with and then graduate more towards these, which end up being about the ocean and helping to people realize about how the air affects, how carbon dioxide affects the oceans.